you're manipulating the. Okay.
Cool. Thank you.
All right. Rehearsal done. I know, yeah. Or else you get some device and you think, okay, I should know how this works, but hold on the side and double click. All set. And you have the mic? As you wish, yeah. I've got to duck
Wait,
out
how
if I
much
want to.
time do we have? It's
Well, it's 1 minute.
quarter,
But-
right?
But they'll be late, yeah. Yeah, I don't know what clock we're going on. But I make it 2 minutes on here, so.
2 minutes, so my clock is okay.
Anyway, the only thing you have to remember is to
Just
press
turn it on.
press the button and it goes
This one?
green. No,
Big one.
and it's green, you're on, red.
Works.
Well, welcome back from coffee. I see everyone is refreshed and energized and ready to go. Yes, yes. Go, go. All right. So, well, we're going to continue our discussions of massive star atmospheres and what we can learn from them. And our first speaker with an invited presentation this afternoon is Lucia Martins from the University, the city of Sao Paulo, and she will tell us about the X-Shoot-U Stellar Library, hot, low metallicity stars.
Thank you, Alex. Can you hear me, everybody? Line fit? I think I turned it on. Thank you for inviting me. Thank the organizers for inviting me. I am inside the X-Shoot-U collaboration, and I am the point of contact for the working group 6, which is a lot of people, but is the working group that is responsible to form the X-Shoot-U spectra in a stellar library. Of course, a stellar library is a collection of spectra of stars, but that's not only what I want to do, actually. It's a little more than that. So why do we care about spectral libraries? And here I'm going to be very biased, because why do I care about spectral libraries? For me, and I'm going to repeat Paul's figure, because every time anybody says anything about stellar population models, this is going to come up. This is the plot from Roy et al. 2013. And it explains why, actually, we care about stellar libraries. And I'm going to take a different view of this than Paul, actually, because I know it's complex to build a stellar population model, but I still have hopes that we can still do it. So to build a stellar population model, now let me see if I don't mix up the buttons. You need an IMF, which means you need to know how many stars of each mass bin are formed when a cloud forms stars. So you have different masses forming. Then you need to know how each of those stars of different masses, different metallicities, they evolve with time. And for this, you need stellar evolution. And in the stellar population modeling, we use the isochrones, which tells you which stars you need for each stellar population age, right? So as the time passes, as the stellar population evolves, you have a change in the isochrone, because the massive stars are evolving and changing. And then this is really complicated, like Paul said. We don't know exactly the IMF. We assume the IMF is universal, but probably it's not. We think we know how the stars evolve, but there are complications, especially in the high mass end, because if you put a rotation or if you put winds there, the evolution is a little different. But even if we knew for sure all this too, we still needed for each point in an isochrone, we had to associate a spectrum of a star to represent a point, and then we sum up everything to get the integrated spectrum, which is what we call stellar population model, right? So for each age, we combine the spectrum of the stars and create a stellar population model of different ages and different metallicities. And what I want to tell you is that one of the key points in this process are the stellar libraries. So the stellar libraries, even if you knew this, if you don't have a spectrum for each point, you don't have a stellar population that is trustable. So you need good stellar libraries to build stellar population modeling. And I care about this because I come from an extragalactic background, and the only way to interpret faraway galaxies where you do not resolve individual stars, and this is most of the galaxies we are talking, right? Faraway galaxies, you only have the integrated spectrum. So this is a fundamental tool to interpret the spectrum of this galaxy. So we need this stellar population modeling. And of course, you can build this empirically combining stars, but when we do this using the IMF and using the isochrones, you get information about your about your galaxy in the integrated spectrum. You get age, you get chemical abundances, you get star formation history. So this is important to learn how to build. And so stellar populations are key ingredients, stellar libraries are key ingredients to do that. And there are two main ways to build a stellar library. There's an intermediate one too, but I'm not going to talk about it. You can build a stellar library empirically, meaning you have a bunch of observed stars that you transform in a spectral library, or you can have a theoretical library, meaning that you build models to create the spectrum of your stars, and then you put this into the stellar population modeling to create a stellar population model. Which one is the best? Well, both, actually. The advantages of real star, the empirical libraries, is that they are real stars. So when you combine the spectrum and put this in a stellar population model, you can be sure that all the features that you observe there are real features and everything should be there. The little problem is that, of course, you have limited signal to noise because they are observed. And you have errors that are intrinsic to the reduction processes, calibrations, inaccuracy of stellar parameters is a main issue. And the most important one is the limited coverage of the HR diagram. So there is no way to run from this. We are limited by the stars we can observe. And for a long time, this meant only stars from the Milky Way. Now we are going away. We are going to the Magellanic Clouds, for example, but still we are limited to the stars that we can observe individually. And this means limited coverage of the HR diagram. Theoretical libraries don't have this limitation, so we can create models for any chemical pattern we want, any atmospheric parameter you want, with infinite signal to noise, any wavelength coverage. Of course, the larger the wavelength coverage and the larger the number of models that you have to generate, more time you need. This is not a problem anymore nowadays. We have big computers to do this, but the physics that we use are still limited, right? So we have to make approximations. We have sometimes to use non-LTE models where we should use non-LTE models. We have to assume that they are plane parallel instead of spherical. I mean, there are a lot of physics that sometimes we have to assume, and this makes the models don't be as good as the empirical. For this reason, most of the models that were constructed historically in the optical, for example, until now, and I'm not talking about the UV, I'm talking mostly about the optical. Most of these models, the famous models that everybody uses, use empirical libraries. The good news is that these models are actually okay. The stellar libraries are actually doing a good job. In this work in 2019, we tested how different stellar libraries, both empirical and theoretical, paired to reproduce the integrated spectrum of globular clusters. I know it's old populations. I know. I'm going to get there. But still, it's a good news, right? It's good news because both are faring pretty well, I would say. Of course, the empirical libraries are better to reproduce individual smaller features, but the theoretical stars are also reproducing well the overall shape of the spectrum. This was also done in a different way by Paula Coelho in 2020. So these two papers actually test what we have so far, and we are in the good track. We are in the right path. So both these kind of libraries are still needed. We cannot choose one of them. If you want individual signatures, individual features, you have to go to the empirical libraries. But if you want to go to very different chemical patterns than the ones we find in our neighborhood, then you have to go to the theoretical libraries. So we need to improve both. Over the years, both have been worked on. We have many different sorts of stellar libraries for stellar population modeling. available in the literature. Some of them are famous, the Ulysses library, Stalib, many of them, the new one, XSL. And what does it mean to build a spectral library for stellar population modeling? It's not just a bunch of spectrum that you just put in there and you use it. You need spectra that are homogeneous, preferentially observed with the same instrument, reduce it in the same way, with the parameters calculated in the same way. You need homogeneity to do this. You need to have only stellar effects, so you have to remove extinction, you have to remove any nebula line, somehow determine the atmospheric parameters homogeneously in the same way, and maybe provide useful measurements like some indexes or something for people to guide their models. This is a few examples of some common libraries available in the literature. This is the Kiel plane, which means you have gravity and temperature, gravity in the y-axis and temperature in the x-axis. The lines are isochrones. So to have a good stellar population models, you need these points. Each one of those points are stars from different libraries. So you need to have points along the isochrone to be able to build that model. And so just for you to have an idea, this one up there is Stalib, and this was the library used by Bourgeois and Charlot 2003 to build their models. So you can see that coverage is very limited, but this is what they had in 2003, right? Since then, many things evolved. This is the Ulysses library, which you can see the coverage is much, much better, but still lots of holes in there. The most recent evolution in this is the XSL library, which was released in 2022. And it represents a next step, both in the sense of coverage, because it's the largest coverage of the HR diagram, although they focused on the old stellar population, so low mass stars, but also in terms of spectral resolution and wavelength coverage. So it's, for extragalactic people, this is really high resolution. I know for stellar people this is not, but for extragalactic, this is high resolution. The coverage in wavelength is very good, and when you compare to all the other ones, it's really hard to beat this. And why am I telling this? Well, because this is the coverage we have now for XSL, which is the state-of-the-art stellar library for stellar population models right now, right? These are, again, the Kiel plane. This is the Kiel plane again, temperature, gravity, isochrones from the Geneva group, different ages. This is 3 million years, 10 million years, 32 million years. So you can see that the coverage for old populations is good, but when you go to younger populations, this is bad. And I divided the stars by metallicity, so the red ones are the lower metallicity, and you can see that it gets even worse if you look at the red point, right? This means that when you generate stellar population models with this library, you are limited in metallicity, limited in ages that you can fit. So this is the safe zone that XSL can do. And you can see that when you go to lower metallicities and you go to younger ages, the coverage is really poor, right? So why is XSL, why is XQ2 and Ulysses important, and how the UV can help us in this sense? Well, I'm not going to describe XQ2 again. Frank already described to you what we did. This is paper 1 with the description of the project itself, but it's optical observations of the Ulysses star, the high mass UV, high mass Ulysses stars. And this is what happens when you put these stars in the Kiel plane together with XSL. So you can see these are the LMC and SMC stars, and they pretty much, I know it's still there are holes, of course, but you can see that the improvement in coverage now is They are really complementary, right? So X22 together with Ulysses is going to create a stellar library that can be much broader than whatever we have available so far. And of course, this is the data release paper. It is already on SPH. You can download and see it. We have lots of beautiful spectrum. They are reduced, flux calibrated, merged, and everything. But this is not a stellar library yet, not for stellar population modeling point of view, right? So we have all this beautiful spectrum, but I knew I was going. So it's flux calibrated. We have sort of calculated radial velocities for the paper too, but we still need to transform this in a stellar library for stellar populations. It needs to have all the tags attached. It needs temperature, gravity, metallicity, abundances, extinction. I need to say which ones are binaries and which ones are not, because despite trying to avoid binaries in the Ulysses program, actually many of them are binaries, and I have to remove them from the sample, or at least tag them so people can know which ones are, which one is binary, which one is not. We have to remove nebular emission lines. We want only the stellar effects. And the ideal thing would be to extend the optical up to the UV, because for younger cell populations, this is what we want to do. So Joachim is going to help me with that, because as he presented, he's determining a lot of these parameters. But if you're working either in the X22 data or Ulysses data or both, and you measured anything, let me know, because what I'm going to try to do is to homogenize everything. I need to collect the data from all of you, from the UV and from the optical, and try to make sense of it all and provide for the stellar population modeler the spectra without redding, without nebular lines, properly tagged with all the information in a way that he doesn't have to do anything, just plug in their models to make the stellar population modeling. So spectra is there, but I need to do much more than just, grab the spectrum and put it available for everybody else. So when I do that, actually, I think this is going to be the next step for stellar population modeling, because Ulysses plus X22 is for sure the highest coverage in hot stars, highest sign to noise, higher resolution of hot massive stars of low metallicity that we have so far. And when we combine this with and this was very fortunate, right? Because XSL just was released last year. So when we combine this, for example, with XSL, this is going to provide the capability of creating stellar population models, both for old and young stellar populations together. So please let me know if you have measurements. Thank you.
Thank you, Lucimara, for this wonderfully clear talk. Do we have questions? I see Ravi.
I had a question about tagging binaries. I mean, are these known binaries, or are they binaries that are inferred from the spectra themselves that were previously unknown to be binaries? And how many are there?
Well, I think they were unknown because Ulysses was trying to target non-binary stars, right? But in the end, some of them are spectroscopic binaries. When you go to high resolution and you look at the lines, you see that they have to, right? I wouldn't say the majority of them are. This is not true, but it's not one or two. There are few of them that are. I really need people to tell me which one, because sometimes you just think it's a normal star, and then when you go try to model it, it just doesn't fit. So sometimes it's really hard to tell if it is a binary or not. Some of them are obvious. When you look at the lines, you can see, sometimes a double lines and everything, but some of them are not. So it's not that easy.
Other questions?
This is super nice, thanks. Do you also need to get rid of all the neutral gas absorption lines from the ISM?
Yes.
Great. I think a few of us in the room can help with that.
Anything you can. In the beginning, I was thinking, well, I'm going to do some work, and then I realized, no, I just, there are a lot of people already doing a lot of stuff. So what I have to do actually is just collect I'm going to be a data collector. I'm going to collect everything and try to homogenize it.
I mean, I don't know if it's possible to model of all the ISM lines, but I mean, they should be narrow enough. You might be able to just interpolate over them.
Yes. I think there are people doing that.
Yes, we can get rid of hydrogen though.
That's perfect.
More questions? Klaus.
Lucimara, I don't think you particularly emphasized Wolf-Rayet stars, right? Because this was never the goal of Ulysses and X-Shoot U. So does this mean if you were to reproduce Paul's empirical template, you would not be able to do this if you were to reproduce the helium-2 4686 or 1640?
If I don't put the Wolf-Rayet stars there, true.
Yeah.
The thing is that I'm not saying that I'm not going to put the Wolf-Rayet in the library. They have to be there.
Yes, yes,
And
yes,
then the
that's, I
problem is
encourage
that
you.
Then the problem is for the stellar population modelers that they have to have isochrones that
Yeah.
take into account the
Yeah.
So I'm going to assume that this part is going to be done by the stellar population modelers. I'm going to provide the Wolf-Rayet in the same way that
Okay.
I'm going to put
Great.
all the rest, and they have to know what to do
Yeah,
with them.
I just didn't see them listed in your spec.
No,
That's why I'm
they're not
asking.
because they are in the, but they are there.
Great, great, thank you.
Other questions? Kat.
Kat Barger, Texas Christian University. This isn't really a question, but just an echoing. So when it comes to the ISM lines, there's also a bunch of CGM lines, and so then you'll probably also want help from the community for that as well. That's all.
Any help is appreciated.
It gets worse and worse.
I know.
All right, Joe, do we have anything online? All right. Let's thank Lucimara again.
On. Yeah.
That'll change it. If you want a pointer, that and wiggle your. Yeah, and the other one. Pretty soon.
We're getting a preview. You all set? Good. All set. Great. The next talk this afternoon, the next invited talk will be from Jon Sundqvist from KU Leuven, who will tell us about some spectacular advances in 3D unified model atmospheres for the winds of hot, massive stars. Jon.
Yes. Yeah, thanks a lot. And we've heard actually a lot about the ways we currently model the atmospheres and the winds of hot, massive stars in the afternoon. Great work, a lot of which I'm myself involved with. I'm not going to talk about that. I'm going to talk about the future. So you can see it as a parallel on Friday. Miriam will give you a great overview about what's the future for observations of massive stars. So you can see it as a parallel. I will talk about the future for the modeling and the spectral analysis of these hot massive stars. So hopefully starting soon. Now, the first thing that you might want to ask here is that, so why haven't we already done this? Why don't we have 3D model atmospheres of hot massive stars? Because if you look at sun-like stars, they're pretty well developed by now. This is, for example, using the stagger code, the density, temperature contrast on the sun. And let's see now if this works. Yeah, here is like an optical surface brightness of a small patch on a sun-like star. These are simulations from Bernd Freytag. And of course, even if you look at, so to say, the major global, perhaps, result of these type of simulations, that's the, in my opinion, perhaps the revision of the chemical yardstick of the universe, the Asplund et al. Chemical solar abundances. They're not so new anymore. Huh? It's like almost 20 years ago now. So they are actually already in the process of doing 3D chemical abundance analysis and model atmosphere analysis of these solar-like stars. So why aren't we? Well, first thing here that perhaps is important for this is that, well, classically, you can think about your low-mass star as, you know, the radiative core and the convective envelope, right? Opposite for a higher mass star, very easy to remember, convective core, radiative envelope. So perhaps the radiative envelope leads to a stable 1D atmosphere, huh? So this has, of course, been prevailing, and it was like, okay, perhaps we don't need it. But there have been, for a long time, strong indications that we do perhaps need these type of 3D model atmospheres after all. Here is just one to the left indication. This is like the macro turbulence that if you try to fit your model atmosphere, your 1D classical model atmosphere to the spectral lines of any given star, you know that you have to add these fudge factors. We call them macro turbulence. They're basically just, you know, some tuning parameters so that we get the broadness of the lines. And in the sun, this was like 2-3 kilometers per second. In the red giant, a little bit higher. Here, as you can see, we can talk about 100 that we need to add. So clearly, this is a strong indication. There are many more. One of them here, this is for a Wolf-Rayet star, where you don't see the underlying hydrostatic core. You only see the wind outflow. And there are strong line profile variabilities, etc. So there were, early on, strong indications. I mean, I encourage you, the community, you try to take your 1D model atmosphere code, fit the nose star without adding micro and macro turbulence. And then you come back and you tell me how it went. Joking a little bit, of course, but not so much. So there are also theoretical indications. So these are hot on the surface, right? So we don't deal with hydrogen recombination in my talk today. However, we have other opacity peaks that are near the surface, particularly this which has been mentioned before, the iron opacity bump around 200,000 Kelvin near surface layers. And it's been long known that this provokes convective and strange mode instabilities there, both linearly and really pioneering work there done by Jianfei Zhang and collaborators with the Athena++ code, who showed in 3D radiation hydro simulations that indeed this creates very turbulent subsurface regions and also surface regions of massive stars with some really nice also analysis of those results done, for example, by Will Schultz, who is here in the audience, who is here at Space Telescope with you now. So these were really, really nice models. They dealt mostly, though, with the subsurface regions. And in these stars, we also know that we actually have strong winds. We have heard a lot about them. They're driven by radiation. So it's actually the radiation force that overcomes gravity, drives them off the star. And they're driven directly, more or less, from the surface. So we need to deal with them also in our models and in our analysis. Now, additionally, here I want to mention this point. And this is that the high luminosity to mass ratio of these objects often notes that even in the subsurface layers around 200,000, you exceed the Eddington limit. And that's because even if you have like the convective instability there, energy transport by convection, or really enthalpy, is actually quite inefficient. So even in typically our O-star models, like at maximum 10% more or less. And this means that the radiative luminosity cannot be lowered by more. So the parcels are actually, they are locally exceeding their Eddington limit. So it's almost like you're driving failed wind outflows from these regions, which might then fall back or might be driven away by the above lying radiation-driven winds, which often referred to also as line-driven winds, because we have to deal with the spectral line transport there and the radiation force from typically thousands of lines. So that's why we need a unified approach to do this. Turbulence, subsurface layers, and then coupled with wind outflows. The way we do this in 1D codes, again, I won't talk about that today. I've seen great talks about this. So the task at hand, we want to start from deep the envelope, say around 300,000–400,000 Kelvin, where it's typically quite relatively nice. We go over, in this case, the unstable region around 150–200,000 regions. And this is no star, so the surface would be around here at 40,000 Kelvin. And then we have the wind outflow. So trying to do this in an approach and see what happens. Typically, this is, I won't talk so much about this. Please just ask me about our simulations methods in order to try to get this all in place. Here are the papers that we have in order to do this and our major assumptions. We will talk about some fun stuff, some first results. Here is an O-star. So this is a 2D cut in a 3D O-star simulation. You see these regions here would be the stable, more or less lower radiative atmosphere. Here you have around 200,000 Kelvin. You see that the instabilities are developed. These are now density contrast map, velocity contrast map. And then you can see that from the surface here, around 40,000 Kelvin, up here, you see that the wind is strongly driven out and actually changes the character of the turbulent layers quite significantly here. So you see you have this interaction between the lower turbulent atmosphere, a lot of blowing, and then you have the line-driven wind acting like a suction mechanism from above, creating a very dynamic atmosphere here, cut in the 3D models. If you now, we move on and we look at some typical overdensities. These are now density isocontours showing overdensities in two characteristic simulation, an O-star, a Wolf-Rayet star. And here you can see this is typically the photosphere of the O-star. You can actually see how the, so to say, the overdensity changes a bit of character here from being very turbulent to the line driving effects, which create these typically filament structures. The WR star has supersonic outflow already more or less from lower layers. That's why they're Wolf-Rayet stars. So you see these filament structures very prominently already there. A little bit of change in character from the subsurface layers, which do not experience a net radial wind outflow. Now, I don't know what forward and back. So the picture that starts to emerge here is that in the lower layers, this is again an O-star as the example, in the lower layers here, we have like a radiative envelope, quasi-stable. We enter the unstable region here, creating a lot of turbulence with high characteristic turbulent velocities. This is now, it's basically shot out. It would fall back. We have like a fountain emerging from the convective, the radiative instabilities in the iron opacity bump region, around 200,000 Kelvin. It's going up. You have your light fountain. So if you drink from above, then you can imagine yourself being the line driving effect, actually acting as a suction effect, catching back gas that otherwise would have fallen back. You have this there, and they will fall back, but you have some line driving suction effect coming from above, okay? So that essentially, I would say, the major picture that would emerge. And then for the various massive stars, it's basically about figuring out the differences here. Yeah? Is the energy transport by convection efficient here? Yeah? Then, of course, you can lower the radiative luminosity such that you don't exceed the Eddington limit, creating less turbulence. Are you too close for the Eddington limit, the L/M ratio? The same thing will happen. That will create atmospheres. If you're very inefficient, so to say, in the energy transport here, and you simultaneously exceed the Eddington limit quite a lot, then you can drive the wind already from these deep layers. That's essentially what happens in Wolf-Rayet stars. Yeah? So this will depend, and likely this is the reason why we have the appearance as we have in the HRD with the typical classifications, WNH, LBVs, Wolf-Rayet, O-stars, etc. Now, oops. So, okay, so here are some key first structural results from these simulations. First, I've mentioned this, very large photospheric and wind turbulent velocities. This is, of course, the non-thermal line broadening mechanism, which we typically call micro and macro turbulence. Of course, it will also affect things like the chemical abundance determinations. You know, again, I take the solar new cosmic abundance scale as the classical example of this. We have actually a significant average density temperature structure around the photosphere because of the turbulent pressure that is created in this. This is illustrated in this figure here, where you see that it's extremely much steeper in a model like fast wind than it is the average structure in our 2D simulation. And this is actually not really an energy transport thing. Again, it's a turbulent pressure in your momentum equation. This is likely to affect things like the surface gravity determination, which also seems to be confirmed by some first test that we have done. There is another thing, and that's the strong density velocity correlation in the wind outflow. And the line driving essentially means that the radiation force goes with 1 over the density, you know, to some power. Yeah? So that means that there is less radiation force on the high density parcels. So when you look at this in the probability density maps, whereas in the subsurface regions here, there's not really a strong correlation. What you really see here is that all the high density material is moving significantly slower than the mean velocity. And this is something we see consistently in the Wolf-Rayet in there. And here is another thing, and that is also something that I know that Will has investigated with the Athena++ simulation, is that we don't find anything like a 2-component medium with clumps that follow some beta law. Not at all. This is more like a probability density distribution that we have with a cumulative distribution function. So typically something like the Wolf-Rayet models, I think it was something like 40% of the mass that is lower than the mean density. So to summarize, there's not much in these first simulations that seem to support the current treatments of inhomogeneous that we do in the 1D or atmosphere code. All right, so let's try to take this toward 3D spectral analysis. Key thing is to move away from the free parameter heaven, that is the 1D codes. In the 3D, we have the mass, we have the luminosity, radius, or effective temperature, if you wish, and we have the metallicity. We can, of course, also spin the lower boundary a little bit. We haven't done that so far, but we could. Now, we have talked a lot about these additional free parameters in the 1D. All of these are emergent parameters in the models that we have here. But of course, I got that, yeah, we shouldn't really call this. I think it was Paul who pointed out to me it shouldn't really be free parameter heaven. It's really a free parameter hella. And also I wanted to say here was something that Tomer Chenard pointed out to me last week, that, you know, I just wish that instead of just calibration of once calibrating a bunch of free input parameters, can't we actually test the theoretical model? So the promise for the future is that, yes, with these we can, because if we can't match, for example, the spectra, well, then we need to, of course, in order to create this, we have to do approximation in the physics. This is probably there, but we have to do certain approximation. There are resolution and stuff like that. But if we don't get out the spectra for a given parameter set, then, yeah, there aren't any free parameters for us to tune anymore. Then there is us going back, try to create a better models. Now, first thing then, okay. So what would the O-star look like if we could actually resolve it? So I give you this. This is the emergent continuum intensity from one of these models, and this would be the small patch on the O-star surface. It's 0.2 in the stellar radius, the total here scale, and as you can see, you have a very dynamic surface. This is the radiation temperature moving there, ranging from, in this case, 35,000 to 55,000, but I have to cut it a little bit. There's a big range of radiation temperatures. Of course, then you have to average this over the full O-star surface and see how these temperature variations pan out. Because there is another thing, and that's a disadvantage we have as compared to those doing this for the sun, Yeah, the sun is just there, so you can actually resolve it. You can see it. We can't resolve our O star. So what we have to do is that we need the quantitative spectroscopy as taught to test the models compared with observations. So from our essentially column models, now we create a full spherical 3D star. So going from this picture to essentially surface brightness, that would look something like that. So doing so, we can put this to test with our post-processing radiated transfer tools and see what comes out. So this is a first illustration, large velocity field, 3D simulated O-star photosphere. These are just two generic optical lines, often used in the O-star regime, oxygen-3, helium-2. And what you can see here, typical things. First, well, they're broad. This is in velocity space. So they're very broad, on the order of 100 kilometers per second or something like that. You can also see that there are effects on the line widths and the shapes. You have asymmetries. These asymmetries and the shifts from line center, also in the photospheric lines, those will depend on the actual parameters of the star, but also on the spectral line, because depending on the formation depth, you might have different characterizations of the velocity field. So a line formed at a certain height in the atmosphere and wind might have a different symmetry and shape than one that is formed slightly up. So if one can characterize this, there is a great potential for testing here by looking at the line widths, the shapes, and the shift from line center. And this, again, it's actually a complete analogy to how this is used for the sun, I'm going to be honest. Now, here is, of course, since we have talked a lot about the UV lines, this is the Ulysses after all. Here is just the carbon-4 line. So another thing that we see in the winds, of course, is that we get a lot of turbulence. So we get a natural softening of this edge. This was mentioned in the previous talk by Alex, for example. This is not really a full line because it's not the full doublets. We have yet to implement this. I've also cheated a bit with the source function here, but you can ask me afterward. But this effect is not likely going to be affected by those revisions, right? We have the softening of the edge. We can create the blue troughs and stuff like that. And this will, of course, also then be powerful tests moving forward. Now, just to give you one first example, I took the optical line here, comparing to now a hydrostatic model average. Huh? So here is now my hydrostatic model average where I just took the average and then set the velocity field to 0. So what you can see is that the lines are much, much narrower, right? And that's your classical 1D micro-macro turbulence that produces this desaturation, the broadening. In this case, you can see that also the equivalent width of the line is changed. Huh? So in this particular case, you could just increase the abundance, or like I did here, I added some microturbulence just on the rats to the 1D model, the average model. They had the same equivalent widths, and then you do the rest with the macroturbulence. That's typically what we do. In this case, the microturbulence was 25 kilometers per second. The macroturbulence needed to get it out was 110 for this particular O star, right? But I don't want to be too hung up of these values because they're ad hoc fudge parameters anyway, so one needs to do this more systematic. What we can say is that there's a very strong, I can say that's already now, that in the models we see a very strong effect on the luminosity to mass ratio, gamma E, when it comes to these type of entangling. These are the typical order of magnitudes that you would expect from a supergiant like this, qualitative, I would argue. So just then finally, just a nice thing for the Wolf-Rayet stars. We only see the outflowing parts. You see what the Wolf-Rayet star would look like if you could actually resolve it over there, right? Oops. No. Okay. Anyway, and then here you see that this also induces a lot of significant variabilities in the line and the continuum. Just the order of magnitudes, this would be the equivalent of a photospheric variability, and this line variability, which are indeed observed in the Wolf-Rayet stars. So this will be other potential tests that we are working on. But that's a little bit, I guess, also for the future. So all right, so yeah, that was basically it from the first multi-atmosphere wind models up and running. We have some 3D package there to explore effects on spectra. Now, key results, we have the very turbulent atmospheres, the large velocity field density variation also in the photosphere. It's no micro and macro turbulence certainly needed. If anything, the velocity fields are too high at the moment. So we will see. Hopefully we can start to do together some quantitative fitting here. The observed line widths, the shapes width, there will be critical tests for the models. 3D effects on chemical abundance, stellar parameter derivations to be explored. I already mentioned the effect on surface gravity. For example, that will certainly be a systematic. And yeah, not much in these simulations seem to support the current treatments of inhomogeneous, what we call clumping in the one-remote atmosphere code. So here we might have a rethinking needed, if you ask me. There are two things I can mention in this because it has come up before. First, there is certainly not any physical justification at this point to assume that all the wind mass is in the clump. This was also empirically touched upon previously by Olivier, right? And the second thing is that not this rho squared effect that we talked about with the recombination line. Yeah, that works for an optically thin line that's formed in a static medium. Huh? But it doesn't work, at least not in these simulations. It doesn't work so much. And that's my intuition. This will have to be further investigated. Tells me that this is a little bit, because the line formation here takes place in the wind. So you have the velocity field effect. And you saw the strong anti-correlation between the density and velocity. So the optical depth invariant is actually not just the rho squared. It's actually rho squared essentially divided by the velocity gradient and taken at a given velocity, but given line of sight velocity. Yeah? So it's not just, so to say, that you can take a rho squared and what is your clumping factor and just assume that, okay, all the clumps follow the beta velocity law. At least not in our simulations here. All right, and of course, yeah, the little bit of a purpose of my talk here also is to I hope I can get during the week some input for suitable tests for models. I mean, what strategic line? This is really first models that we present on these types, right? What strategic lines, what type of stars, the spectral windows from the Ulysses X shooter, it will be extremely beneficial. We have talked about things like the UV iron forest, but there are also optical lines, there are wind lines, and there are plenty of other things to explore here, including then systematics that will certainly be different when you do your spectral analysis from these type of models versus when you calibrate and calibrate again and calibrate again our 1D model atmosphere code. Yeah. Thank you.
Wonderful, Yun. Thank you very much. A lot of things to think about. A lot of advances coming at us quickly there. Are there questions? Let's start with Ed.
Do you expect much difference from the center to the limb, and or is it pretty much the same?
If there are different in the center to limb, like the limb darkening,
yeah, that's
compared
right.
to the 1D
Do you put that in?
I personally, we have not in detail investigated this, so it's a very good thing, and it's something we should do, and I will definitely do it now, so thanks for the question. Intuitively, I can say I expect this to be a second order effect because there is, across the surface here, there is a lot of averaging going on. Huh? So I do expect this to be a second order effect, but don't hold me on that in 2 years.
Another question. Rotating stars have a different temperature of the equator than at the pole. So therefore you might have to consider admixtures of different temperatures.
That's a very good question, and there is one thing which I didn't say, and these are essentially local models. So we have to do a full global model to do this temperature variation in the spin. And then we have to sacrifice certain other effects like resolution, etc. So, but it's on our list to do that. What we can already now do with the local models is that we can spin them up to, say, 70%. Because this gravity darkening effect is typically just effective when you have something which is like 70% or more of the critical rotation, or the critical rotation speed. So up to that limit, we could already investigate it with this. But faster than that, for example, then we need to go to global model, which is something we're working on, but we're not quite there yet.
Hi, Justin Campbell-White, Isa Garking. Thank you, very interesting. I just had a curiosity about your observational tests and what kind of resolving power you think you would need for specifically the line shapes, like how you would actually see that before it just got smeared out by the instrument profile.
Yeah, it's a great question. That's why I asked this myself to Frank before. Yeah, my suspicion is that in general, we will need a little bit higher than 10,000, but it depends on the parameters. Because if you have a slowly rotating star, then I think you need more. But Jorik assured me that that's actually the case as well. If you have a faster rotating star, though, then we need to introduce the spin, and then we will see how it interacts, right? And then you can get away with a little bit lower. So it actually will depend, I think, on the spin rate of the star, because if that's going to set the major broadening or not. Yeah. But if I'm going to be honest, in this, that's in the optical. I mean, Alex showed some UV spectra of the iron forest, which looked very promising in that respect as well, I must say. So.
Very impressive work. I'm wondering, how would the magnitude of these effects on basically on the line profiles compare to the case when you had a binary star that has an, say, yet unknown companion, not strongly interacting, but just, you know, a companion? Could this companion also create basically effects on the profile that could be comparable and would be very hard to separate?
You have to put it again. It's now I'm speaking from a little bit of speculation, intuition, right? I think that if you're quite wildly separated, it will be fine, because you're going to interact with the outermost wind outflow. So you're pretty much, for most stars, reasonably far away from the line-forming region, which takes place closer to the star. Except for perhaps, you know, like the outermost parts of the UV line profiles, where you can induce variability from that. Yeah. Now, if you put the stars closer together, then we're entering a new ball game, and that's a very interesting thing. It's actually something we're trying to investigate together with Uksana's group and doing models for these type of interaction. Then that might be the dominating effect in that sense. But then again, this is to be developed. That would be my intuitive.
Thank you, Yun. Let's thank Yun again. He's obviously going to be very busy for the next little while.
I didn't even turn it off, you know.
All right. For our last talk of this afternoon, we're going to have a contributed presentation on some spectacular work on the very metal-poor stars and what Ulysses and other work can do for that. This is going to be, the other work is due to Grace Telford, who is at Princeton and the Carnegie Observatory. So Grace, please take it away.
Thank you very much for that introduction, Alex, and thanks so much to the organizers for having me here today. So yes, today we have been hearing about how the high mass star component of Ulysses has targeted the low metallicity stars, primarily in the Magellanic Clouds. But my focus is on very metal poor O-type stars, and that just means stars that are even lower metallicity than we can access in the SMC. And so today I'd like to talk about what Ulysses and other programs have already been able to do in this regime, and also what observations we still need. So 2 years into the JWST mission lifetime, we have already seen this population of low metallicity galaxies at high redshift that have pretty unexpected properties. And there's still a lot of intense interest in the extragalactic community in understanding their contribution to cosmic reionization. So in these early galaxies, it's low metallicity O-stars that are producing feedback that regulates the formation of new stars and can also carve channels in the dense ISM through which ionizing photons produced by O-stars in those galaxies can escape. And so to understand how all of those processes work in detail, we need models of stellar spectra and evolution that are calibrated to observations of individual massive stars at low metallicities. So we've heard from many speakers today how Ulysses combined with the XSHU data set have given us exactly the kind of data that we need to do that sort of work, really rigorously calibrating models at 20 and 50% solar metallicity, thanks to this enormous data set of far UV and optical spectra of hundreds of O-stars in these two very nearby star-forming galaxies. Now, we also heard that Ulysses extends to lower metallicities as well. So Ulysses obtained new G140L spectra of 6 O and B type stars in these two star-forming dwarf galaxies that are outside the edge of the local group. So these are something like more than 20 times farther away than the SMC. And so these 6 stars took about 10% of the Ulysses orbits that were devoted to the high mass stellar component. So these are expensive targets. Now, to complement this, Ulysses also compiled an archival sample of low metallicity O and B stars, coming up with 27 in all that have been observed in the far UV in galaxies below 20% solar metallicity. Now, this is about an order of magnitude fewer stars than in the Magellanic Cloud sample in Ulysses. But these very low metallicity O stars are very important because we really don't have much information about how stellar astrophysics changes in this low metallicity regime. And this is exactly the metallicity range that's most important when we are trying to model these high redshift galaxies that drove cosmic reionization. So this is the motivation for my work on a pilot sample of 3 of these very low metallicity O stars. So I'm going to show you some results from my own work to basically illustrate what we are able to learn about these distant, very low metallicity stars by observing their far UV spectra. And so these 3 stars are found in galaxies from 3 to 14% solar metallicity in terms of their gas phase oxygen abundance. And our team observed these 3 stars with COS, and these spectra are all included in that Ulysses archival sample that was mentioned earlier. So we chose to use the moderate resolution G130M and G160M gratings, which give us better than 50 kilometer per second resolution. And this is important because it allows us to detect weak photospheric features and also resolve detailed line profiles. And so a good example of these important but weak photospheric features is this forest of highly ionized iron transitions. So you can see in the most metal-rich of these 3 stars down here, that is not noise, that is actually iron 5 absorption that we are seeing. But in these lower metallicity galaxies, the continuum becomes quite featureless. And so we're getting empirical constraints on the iron abundances in these stars and also on the shape of the ionizing spectrum, because iron is the dominant opacity source in the extreme UV. Now I'm going to focus in on one photospheric absorption feature in these 3 spectra here. This is a complex of 6 closely spaced carbon-3 transitions around 1176 angstroms. And the black lines here are showing the observations. And for comparison, the gray in each panel is a stellar spectral model that is matched to the observed profile in equivalent width. So the stellar rotation will act to broaden and smooth these model profiles, but will not change the equivalent widths of the lines. And so I can apply a rotational broadening kernel and fit for the projected rotation speed that best reproduces the observations. And I find that both of these very metal poor O stars, below 10% solar metallicity, have very high rotation speeds. And so to put these numbers in context, this figure shows my observations as the vertical black lines in this figure. And for comparison, I'm showing the observed cumulative distribution of V sin I of similar late O dwarf stars in the Small Magellanic Cloud at 20% solar metallicity. And from this plot, we can read off that the 2 very metal poor stars here with high projected rotation speeds are rotating faster than 90% of similar stars in the SMC. And so this is a small sample, but this result strongly suggests that the low metallicity fast rotators are drawn from a different V sin I distribution than the SMC counterparts. And this is the first support we have for the theoretical expectation that fast rotation is more common at these very low metallicities. And if true, this is important to include in stellar evolution models because rotation induces additional mixing and boosts surface temperatures and lifetimes, which will boost the lifetime ionizing photon production of these O stars. Okay, now moving to a different part of the FUV spectra, I'm showing 2 different doublets that are sensitive diagnostics of the stellar winds, which we've been hearing a lot about all day today. So as Yorick nicely highlighted earlier today, the mass loss rate really strongly impacts the evolution of these massive stars and also their ionizing spectra. So it is important that we understand how mass loss rates scale with metallicity, but we don't have very good constraints given the small sample of observations in this regime. So in these spectra, you can see the strongest wind profile is in the most metal-rich star down here, but the profiles become very weak and extend to lower velocities in these lower metallicity stars. But to quantify these mass loss rates and terminal velocities, we actually need to do some detailed modeling of these far UV spectra. And we also need optical spectroscopy to break degeneracies with the stellar temperatures and surface gravities. And so I have used the KCWI instrument on Keck to get follow-up optical spectra of these 3 stars. And at this R of 4,000, you can clearly separate nebular emission lines from the broad stellar absorption features, and you can detect these weak helium-1 and helium-2 lines that tell us the stellar temperatures. And so now I have all of the data that I need to fit new stellar atmosphere models running with the power code to reproduce simultaneously the observed profiles in the far UV and the optical. And from these best fit power models, we are going to be able to measure the mass loss rates from these stars and also constrain the detailed metal abundances, carbon, nitrogen, oxygen, and iron. And we can also extend these best fit spectral models across the full wavelength range to predict ionizing spectra that are actually informed by observations of O stars in this very low metallicity regime for the first time. So we've been able to learn a lot from just 3 stars, but this is clearly not enough to do a rigorous calibration of stellar models the way we're going to be able to do with the LMC and SNC samples from Ulysses. So returning now to the archival low metallicity galaxy massive star sample that Ulysses compiled, not all of those observations are actually sufficient to do the kinds of measurements I've been describing. For that, you need wavelength coverage from 1150 to 1750 angstroms to make sure that you get all of the key diagnostic features. And you also need moderate resolution spectroscopy in at least one grading so that you are sensitive to those very weak and challenging to detect absorption features in the low metallicity star spectra. So if we look at this archival sample and find all of the stars that meet those criteria, we find 17. And the colors here just break the host galaxies down into roughly 5% and roughly 10% solar metallicity. And you see from this figure that we are not spanning the whole range of spectral types and luminosity classes here. We're missing all of the hottest stars, so all of the most massive stars that are dominating the ionizing photon production of a population. And we're missing the latest type, lowest mass O stars. So these are most common and our most common supernova progenitors. So to remedy the situation and better populate this parameter space, I am leading a new large treasury program with the Hubble Space Telescope called TEMPOS, the Treasury of Extremely Metal-Poor O-Stars. And we are strategically building on this archival sample from Ulysses to obtain new COS observations, either complementing existing spectra for 8 of these stars, or observing new stars that have been recently identified in some cases for the first time in the far UV. And so again, we need the far UV spectra to be able to analyze these stars, and we also need optical spectroscopy to complement them. So we are also using the DEMOS instrument on Keck. It's a multi-object spectrograph to observe optical spectra of all of the TEMPOS targets. And so when the new data being collected this year are complete from both HST and Keck, TEMPOS will provide the best possible coverage of this O-star parameter space at 5 and 10% solar metallicity, given technical feasibility and our current knowledge of the O-star content of these nearby galaxies. And combined with Ulysses and X-shooting Ulysses data, we will have the best possible calibration data set across 5 to 50% solar metallicity, spanning the full range that's relevant for modeling high redshift galaxies during the epoch of reionization. Okay, I think I'm out of time, so I'm just going to leave up conclusions and take questions. Thank you.
Thank you, Grace. Spectacular work. Really, really exciting. Questions? I see Yorick.
Very, very interesting. The 3 stars that you're modeling with power,
yes.
You didn't give results, so I guess it's still ongoing.
It is still ongoing.
But the wind velocities, you can already say something. Are they low or are they high?
They're very low.
Very low?
Yes. So I do have preliminary results. I do not believe the error bars I have right now. This is why I'm not showing you results.
Hundreds of kilometers per second?
Hundreds of kilometers per second. My best models for 2 of those stars have 300 and 500 kilometers per second right now.
It's really interesting.
It's very low, yeah.
Yeah, but it's interesting.
Mm-hmm.
Well, thank you. This was a very exciting talk.
Thank you.
I was very interested in your spectra. The very low metallicity are rapid rotators, you say. And rotation is leads to excessive nitrogen enrichment. Mm-hmm. And I didn't see evidence of nitrogen enrichment in your stars.
No, I do not see evidence for nitrogen enrichment in those 2 stars either.
That's weird.
It is weird. It's also true that the nitrogen lines are just weak, right? They are very low metallicity stars, and if you look at the gas phase abundances in these very low metallicity dwarf galaxies, you see that they are often suppressed in their nitrogen to oxygen ratio relative to solar. So they're starting out with even less nitrogen than a Milky Way star. Yeah.
I have to think about that.
I know.
Thank you.
Yep.
Thanks, wonderful work. So I was wondering, because you quoted very high rotational velocities, and at that metallicity, I would expect chemically homogeneous evolution from stellar evolution. And have you checked the surface composition of these stars? Because, like, do they have an enhanced helium, or can you measure that from your spectra at all?
Enhanced helium, you asked?
Yeah.
So for those two low metallicity stars, the uncertainties on the surface abundances are quite high, so I can't strongly rule out any helium enhancement, but I don't see glaring evidence for it either. I'd be curious to talk to you more about what level of helium enhancement would be indicative of
We should
CHE.
definitely talk about that. Yeah, thanks.
Thank you.
Joe, can we go online now?
Hi, Paul.
Hi, Grace. Great talk and beautiful UV and optical data. I guess the only question I had really is about the application, let's say, of these local metal poor objects, which we know the oxygen abundance. We have some hints about the iron abundance. In respect of the high redshift universe, because of course, high redshift, we get oxygen from James Webb, but we suspect iron is very low because it's very early on in the universe, and therefore there's been not enough time for the iron to, and production through type 1a supernovae to really kick in. So what one suspects that the high redshift galaxies will have a high alpha to iron ratio compared to potentially things in the nearby universe which have had a much longer duty cycle to produce the iron.
Yep. Is that just a concern, or is that a question?
Yeah, I guess it's just a concern around the applicability of our metal poor local galaxies to the redshift 8s and 9s and 10s.
Yeah, totally. I agree with this concern, right? But we do not have examples of very alpha-rich, low metallicity stars in the nearby universe. So this is basically the best that we can do. And I think we just need to be careful in applications and not make naive assumptions about alpha to iron ratios.
Yeah. I agree.
Thanks, Paul.
Miriam.
Hi, so I have a comment and a question. The comment is that IC 1613 is not so metal poor.
In its oxygen abundance, it is.
The
Probably
oxygen
not in
is
its
very,
nitrogen.
very metal poor. That's why we started looking into that galaxy.
Yes,
but
I am
not the
familiar with
iron.
your work there. I totally agree.
It's not only me. And the second one relates to the terminal velocities. So you said you have values, but maybe they are only upper limits, or you see saturated P-Cygni profiles.
I would not, no, they're not saturated P-Cygni profiles, but I am running power atmosphere models, and I vary the terminal velocities, and I find that I can actually reproduce the observed shapes of these very, very weak wind profiles, but only for a specific and relatively narrow range of terminal velocities. So it's maybe not the most slam dunk result, right? Because as you say, it's not a saturated P-Cygni profile, but it's not just a limit either.
It will give you a lower limit, but if your ionization balance is not correct, then you don't know if the wind is much faster, but you're just not seeing it because the lines are too weak. So you don't see the outflow.
Given the ionization balance from
given the ionization balance from power, then yeah, sure, then you can derive it. But yeah, that's given that.
All right. Are there any final thoughts on this? Obviously, a very interesting paper. If not, let's thank Grace again.
All right, thanks, Alex.
Now we come to the part of the afternoon where we have poster pop-ups. And I'm as excited as you are to see how all this is going to work. But I think we're going to have anyone who wants from our list of 6 people. Yep. 6 people come up and give us their elevator pitch on their poster, and so that we can put face to a name and can come and find them at their posters sometime else during the meeting and find out more about their work. So,
Are they downloaded?
sure hope they are. So we're going through it in an order that I have here. Cool. Oh my God. Not sure.
Bushixen online? So in the in the program, there's a list of 6 poster presenters who are supposed to come do the poster pop today. If you can just come here and give your elevator speech. This would be Sen, Sauer, Chu, Horton, Walter, and Nyack. Nobody else is here. Interesting. Okay. Well, we can just have whoever's
I see a couple people. And anyway, Fred is first up. He's the man who's going to show us how to do it here. That's
I'm going to change the direction of the meeting here. We'll go back to cool stars. Okay, I have 1 minute, right? In less than that. One thing I've learned in 45 years of observing T-Tauri stars, many things I've learned in 45 years observing T-Tauri stars, is that they have inflows, they have outflows, they have magnetic fields, they have magnetic flaring, they have ultraviolet excesses and infrared excesses. They have dark spots, they have hot spots. And sometimes they do this all at the same time. And then they rotate too, and then they vary on longer time scales, stochastically. So this is what makes it difficult to interpret single snapshot UV observations, or even a series of UV observations over a few rotation periods. We need to put these things into context. So what I have up here, poster 3, way back in the corner. Poster 3, remember that number, is just an overview of some of the stuff I've been working on. I've become enamored with, and I should say distracted by, the test light curves that show us that these things vary on very short time scales. Here's a derivative in millimagnitudes per minute. In black is the T-Tauri star. You can read the details on the poster. You can see flares up there, flare statistics. Here's a test light curve showing in blue when HST observed as part of Ulysses, in purple when I got optical spectra. I'm not going to solve any problems tonight, or today, or this week. We have a premise that we can deconstruct these pre-main sequence stars into 4 components: telephotosphere, flares, accretion, and optically thick circumstellar material, occulting the star on occasion. I have yet to convince the review panel that this is the way to go, but I'm still trying. And you can Can you scroll up just a bit? The spectra are down at the bottom. Perfect. We have a whole bunch of spectra from Chiron at 30,000 resolution. This shows this shows differential spectra offset by the test magnitude. When it gets brighter, yeah, those lines get wider and they're bigger. That's the accretion. Here's H alpha. It's a mess. You see inflows and outflows. And let's just take a look at it. Poster 3.
Thank you, Fred. Who's next? Show how to do it. Don't make me ask. Here we go. All right. You're the next contestant. Ah. Okay. Let's get it up there. Is that Arturo?
Oh, I see it. I was looking at last name first. Never mind.
Arturo, take it away.
Yeah. So this has not much to do with current observations. It's completely computational numerical simulation. We are here dealing with a high resolution, so we include the grid here to show that we have we're very close to the star, and we are simulating the star and the whole disk for should be about 600 solar radii, and we have the stellar truncation radius for the stellar magnetosphere, and we have introduced planets to the simulation. My supervisor, Shahwan, had a paper before only dealing with the magnetosphere accretion, and in here we have introduced a very large planet here in the poster, but we can introduce any planet we want. So we have these very nice images, these very nice close-ups to this 10 Jupiter mass equivalent planet, which has accreted some material. So we have 3 results that we want to share. So if we could zoom it. Yeah. So our first idea was be able to to detect the planets. So since these are very large planets and we have accretion towards the star that we can measure, we thought that maybe we would be able to see a change in the accretion, and we expected to see a peak here. However, we are not able to see it yet. We get a peak in the periogram, but it has to do with a bubble, we think. Number 2 would be to study the torques that the planet is feeling and connect that with planet migration. We care about hot Jupiters. In this case, the planet is at very close to the star, and what forces would the planet feel, and we are able to at least say that it's not a random torque that it's feeling. Number 3, and the most surprising one, is that our planet is able to get a circumplanetary disk around itself, and it's able to steal some of the magnetic field from the star, and it gets to a pretty strong level value comparable to the star, and it's able to show features of a bow shock as it moves around the disk. So we are now dealing with a planet magnetosphere, and here we did some tests to confirm that this is actually a circumplanetary disk by the planet's own gravity, and we are deriving some criteria to when we would have a circumplanetary disk and where we would not get it. for example, for a very low mass planet, we don't see these features forming, for example. And that's all.
Thank you. And there's lots to look at in that poster, so please go by and check it out. Thank you.
Hello.
All right, Prasanta, take it away.
Yeah, thank you. Good afternoon, everyone. In these posters, we are mainly going to present the FUV spectra using UVIT of T Tauri stars, mainly the TW Hydra and HD 202917. So throughout these posters, we are just trying to convey that whether we can study the variability in T Tauri stars using the low resolution spectroscopic mode using UVIT. So when we look into the archival data of TW Hydra of UVIT, we saw that like spectacular features of carbon 4 lines, and it matches well with the IV spectra. Then even we also compare it with the different epoch of observation using HST as a part of the Ulysses target. And we saw that if we degrade the spectra of HST to the resolution of UVIT, we can see the variability not only in the line luminosity, but also in the continuum. So we propose for a couple of classical T Tauri stars, including TW Hydra, RW Auriga, and a weakling T Tauri star HD 202917. But unfortunately, we got time only for the HD 202917, and we got only 2 epoch of spectra. From the spectra, we see that, okay, it can nicely detect the carbon 4 line, but the problem arises because the source is very faint, so we get very high error, despite we have like more than 5 hours of integration time. So yes, we do observe or study the variability in T Tauri stars using UVIT, but we have to focus on the bright stars. So this proposal cycle, I'm going to propose again for TW Hydra and a couple of more T Tauri stars, and hope to get the time. So I'm gonna share the poster in the Slack. If you have any doubts, please come to me. You can message me. Thanks.
Wonderful. Right. Do we have any other takers? You are April. Come on down.
This is students' summer program. So this is a super bubble, N57. So there are OB associations here and there. And there's an X-ray emission field of this super bubble, and also another X-ray emission source up there. And that's a non-supernova remnant. Okay. So the question is this X-ray emission due to purely caused by shark stellar wind, or it's a supernova remnant there? So there are 2 suggestions. One that says it's a supernova remnant, one says it's pure stellar wind. So there are, based on 3 pieces of evidence, that we think it's a supernova remnant. So this is a shell spectra in mapping this super bubble. You see the line splitting. So it's an expanding shell. It's expanding all over the place. So it's a hollow shell. So no reason for the stellar wind to be confined within the central region to reach all the way to the end. So it's not. And here's the HST image. You see this sharp filaments here? That's the SNR shock. Okay, that's not, steel wind doesn't do that. Okay, the third piece of evidence is here's the UV spectra, silicon 4 and carbon 4. 3 sightlines, 1, 2, 3. And this one is only one that shows this component. And these 2 red lines, these are the H alpha velocities, which shows the front side and back side of the superbubble. And this line, this component is clearly blue shifted from the approaching side of the superbubble. So it's the SNR shock interior kind of coming toward us. So we think it's a supernova remnant inside the superbubble. So that's it.
Thank you. That's exciting. April, tell us about your poster.
Thank you. All right, I'm April, and I am from Texas Christian University, and I'm a grad student there. I did my poster on some work that I did for my master's thesis last fall. So I am studying the properties, or the physical properties of the Magellanic Stream using the Ulysses data set. So the unique property about the Magellanic Stream is that it's divided into 2 different filaments. There's one that's at a higher metallicity, shown by the red line up here, and then a lower metallicity one, shown by the green line. And because they have different chemical compositions, it is assumed that both of the filaments have a different origin, with the lower metallicity filament being traced back to the small Magellanic Cloud, and then the higher metallicity filament being traced back to the large Magellanic Cloud, and then specifically to the 30 Doradus region that is there. So I selected 4 different sightlines from the Ulysses program that are around the predicted location of the Magellanic Stream from the Nider et al. 2008 paper. What I did is I looked at the H1 emission and kind of constrained the kinematic bounds of the LMC's disk and the predicted location of the Magellanic Stream. And using those velocities, I looked at the low ionization species in the Ulysses spectra for signatures of the Magellanic Stream in the data. We found that the Magellanic Stream does show up in the data, which means that it is on the near side of the LMC's disk. And we also determined properties like column densities, kinematic widths, and central velocities of those components. So then going forward, I want to add these 4 new sightlines to this project and perform the same type of analysis to better quantify the results that we're seeing for the original 4 sightlines. Thank you.
Thank you, April. Perfect. Go and see her poster. Now, my list is now incomplete, and I'm in chaos here. Are there any other poster presenters who would like to sell us on their poster today? Yes, Dorot. Okay. We have a video. Okay, we're not sure if we have the video, but we will find it and we will play it at another at the next occasion. All right.
We have time on tomorrow and on Wednesday as well for more speakers. We can find the video and play it then. And I'm updating the Google Doc agenda accordingly. So everything on the Google Doc, the Google spreadsheet, sorry, is up to date. And I think this concludes our first day. So we convene tomorrow at 9 a.m. Reminder, we have this hands-on session tomorrow afternoon, and I hope many of you will attend. I think it should be really interesting. Joe, Rachel, and Elaine have prepared some notebooks to go through, presentations, etc. It's quite extensive. And also Rachel, I think, posted some places to eat dinner tonight. I think in the general Slack channel or random Slack channel. Random Slack channel, yeah. So thanks everybody for attending the first day, and I'll see you all tomorrow.